Okay, welcome back for Phys 112 class, electromagnetism. We've already done chapter 1 to 8. Today we'll look at chapter 9, electromagnetic induction. And that's what we're doing immediately. So today we're looking at electromagnetic induction. So please write down subheading, basic concepts of electromagnetic induction. Basic concept of electromagnetic induction. Basic concepts of electromagnetic induction. Class, in electromagnetic induction, we are now bringing in what? Both electric field and magnetic field together. So how can we induce charges with the help of electric and magnetic fields? What we're looking at under electromagnetic induction. We've already studied electric field separately. We said electric is a region of space where what? One charge causes what? Electric force on another charge nearby. Talked about the magnetic field as well. It's a point where we have magnetic effects occurring. So class, when we now bring the two together, we're going to be looking at the parameters that can entail here. The first parameter we'll look at right now is induced EMF. Induced what? EMF. That is induced electromotive force. Induced electromotive force. EMF means what? Electromotive. So we're looking at induced electromotive force, induced EMF. Induced EMF. And under that, to understand induced EMF, we're going to write down Faraday's law. Under induced EMF, we write Faraday's law. Faraday's law of electromagnetic induction. We properly explain the concept of induced EMF for us. Faraday's law of electromagnetic induction. We properly explain the concept of induced EMF for us. States that the induced EMF and induced current in a coil, Faraday's law states that either the induced EMF and induced current in a coil is due to the changing amount of magnetic field cutting through the coil. Is due to the changing amount of magnetic field cutting through the coil. So that the induced EMF and the induced current in the coil is due to the changing amount of magnetic field cutting through the coil. Is due to the changing amount of what? Magnetic field cutting through the what? Through the coil. That is the quantity of induced current and induced EMF. That is the quantity of induced current and induced EMF are determined by the rates. That is the quantity of induced current and induced EMF are determined by the rates at which the number of field lines changes. That is the quantity of induced current and induced EMF are determined by the rate at which what the number of what field lines changes. Determined by the rate at which the number of field lines changes. Note that the number of electric field lines passing through a given surface is measured by the electric flux. The number of electric field lines passing through a given surface is measured by the electric flux. The number of electric field lines passing through a given surface is measured by the electric flux. The number of electric field lines passing through a given surface is measured by the electric flux. Note that when the number of magnetic lines, note, when the number of magnetic lines passing through the loop increases, when the number of magnetic lines passing through the loop increases, as the magnet keeps moving towards or away from the coil, when the number of magnetic lines passing through the loop increases, as the magnet keeps moving towards or away from the coil, when the number of what? Magnetic lines passing through the loop increases, as the magnet keeps moving towards or away from the coil, when the number of magnetic lines passing through the loop increases, as the magnet keeps moving towards or away from the coil, this will lead to what? Conduction of electrons in the coil. This will lead to conduction of electrons in the coil, and energy is generated for the moving electrons, and energy is generated for the moving electrons, and energy is generated for the moving electrons. And energy generated for moving electrons. Class, the bottom line is that Faraday's law of electromagnetic induction helps us to determine the magnitude of induced EMF. Faraday's law of electromagnetic induction helps us to determine the magnitude of the induced what? EMF in a coil, where induced EMF represents what? Electromotive force. Electromotive force, and the formula for the electromotive force is what we have on the board. Formula for electromotive force is what we have on the board, where N represents the number of turns, D means changing. This symbol stands for magnetic flux. Just like we have electric flux, we also have magnetic flux. And T is time. So what this means that if we get the ratio of the change in magnetic flux to the change in time, we can get the induced EMF. Just like electric flux is talking about the what? The amount of what? The electric field lines, the rate at which the electric field lines flows in a region in space. Same thing applies for the magnetic flux, talking about the magnetic field lines, also known as magnetic lines of induction. So class, with this formula, you could be asked to find the magnitude of induced EMF in a coil. And the magnitude of an induced EMF is minus N, where N represents number of turns, change in magnetic what? Flux, all over change in what? Time. Class, magnetic flux on its own, the formula for magnetic flux is magnetic field B times area. Remember, the formula for electric flux is EA. Do you remember? That will not say cos theta if there's an angle, or just E. So if electric flux is electric field times area, I'm trying to make you remember from what you know to what you don't know. If electric flux, electric field times, it also makes sense that magnetic flux is what? Magnetic field times what? We all know that magnetic field is represented with B, right? What is the unit for magnetic field? Tesla, right? By the area. So we have that. So use this to remember this, and you are good. Class. Right now, there are three ways in which the magnetic flux through a coil can be changed. There are three ways in which the magnetic flux through a coil can be changed. There are three ways in which the magnetic flux through a coil can be changed. Three ways in which the magnetic flux through a coil can be changed. There are three ways in which the magnetic flux through a coil can be changed. Three ways in which the magnetic flux through a coil can be changed. One, we have changing the angle between the direction of the magnetic field. One, changing the angle between the direction of the magnetic field B and the plane of the coil. One, changing the direction. Sorry, changing the angle. One, changing the angle between the direction of the magnetic field B and the plane of the coil. One, changing the what? Angle between the what? Direction of the magnetic field B and the plane of the coil. One, changing the angle between the direction of the magnetic field B and the plane of the what? Coil. Two, changing the magnitude of the magnetic field B within the coil. Two, changing the magnitude of the magnetic field B within the coil. Changing the magnitude of the magnetic field what? B within the what? Within the coil. Changing the magnitude of the magnetic field B within the coil. Three, changing either the total area of the coil. Three, changing either the total area of the coil or the portion of the area that lies within the magnetic field. Three, changing either the total area of the coil or the portion of the area that lies within the magnetic field. Is anybody with their past question here? I want to bring question from this Fridays. Are you a past question? Open one, Three, changing the what? Either the total area of the coil. Three, changing either the total area of the coil or the portion of that area that lies within the magnetic field. Changing either the total area of the coil or the portion of that area that lies within the magnetic field. Class, what we just looked at is Faraday's law of electromagnetic induction. Because our subheading is electromagnetic induction. Let's now look at Lenz's law. Lenz's law of electromagnetic induction. We have two major components of this electromagnetic induction: Faraday's law and Lenz's law. And also look at the difference between Faraday's and Lenz's law. What does Faraday's law help us to do and what does Lenz's law help us to do? So Lenz, L-E-N-Z. Lenz's law of electromagnetic induction. Also take question. Calculate the electric flux on the surface of a rectangular plate. Take this question down. Calculate the electric flux on the surface of a rectangular plate. Calculate the electric flux on the surface of a rectangular plate. Are you there? Calculate the electric flux on the surface of a rectangular plate, 20 centimeter length and breadth 15 centimeter. Calculate the electric flux on the surface of a rectangular plate, 20 centimeter length and breadth 15 centimeter. 20 centimeter length and breadth what? 15 centimeter. Place an electric field of 350 Newton per coulomb. Place in an electric field of 350 Newton per coulomb. Place in an electric field of 350 what? Newton per coulomb. Deal with that one while I find the main one I'm looking for. Where are you? Where are you? Where are you? Where are you? So you should calculate the electric flux, right? I believe you know what to do there. Between that one, I'm looking, there's another question I'm looking for. What year did that question come out? Faraday's law. Okay, I think I've seen it. 51. A coil of 600 tons. Write this question down, please. A coil of 600 tons. A coil of 600 tons. Class, did I tell you the unit for magnetic flux? It's measured in Webers. Measured in what? Webers. Please take note. Unit for magnetic flux is what? Webers. Webers. Please take. A coil of 600 tons is traded by a flux. A coil of what? 600 tons. A coil of 600 tons is threaded. Needle and thread now, threaded is traded by a flux of 8.0 times 10 raised per minus 5 Webers. Class, when you see Webers written as WB, W what? So the minor right thing for WB is traded by a flux of 8.0 times 10 raised per minus 5 WB. WB means what? Webers. Are you there, class? If the flux is reduced to 3.0 times 10 raised per minus 5 Webers, if the flux is reduced to 3.0 times 10 raised per minus 5 what? Webers, that's WB, in 0.015 seconds. In 0.015, find the induced EMF. Find the induced EMF. Find the what? Induced EMF. Find the induced EMF. Well, this is how we can be questioned. I intentionally brought from the past so you can see that. So when you see your test and your exam question, there's nothing better to direct us than those two. Your textbook and your exam question that has been said before. That's the best form of direction. So class, before we go to Lenz's law, I think you can quickly take this example under Faraday's law. We ask to calculate the magnitude of the induced EMF. Class, the formula says induced EMF is minus n, where n means number of tons. How many tons did that person give us? 600. Number of tons is 600 tons. 600 tons, yes, traded. Class, change in magnetic field means a magnetic flux. Change in what? This symbol is magnetic flux, right? Change in magnetic flux must be final magnetic flux minus initial magnetic flux. So magnetic flux 2 minus magnetic flux 1, which was first mentioned 8.0, right?
Yes.
These are our initial magnetic flux. Excuse me. And these are final magnetic flux. So it is what? Final minus initial. These are already at time plus. They didn't give us two different time intervals. They didn't give us the change in time, which is 0. So the t within 0.015 seconds, they're giving us the time interval already, right? So let us apply. Don't forget there's a minus here. So we're going to say minus n is 600 into brackets. B2 minus B1, that's 3.0 times 10 raised to minus 5, right? Class, they both have minus 5, right? So let's just say 3.0 minus 8.0. Everything times 10 raised to minus, just put only 1 times 10 raised to minus 5. Because they both have 10 raised to minus 5, 10 raised to minus. So whatever, when we subtract this minus this, our final answer will be multiplied by 10 raised to minus. All over, what is our time? 0.01. Our time interval is 0.015. So class, minus 600, 3.0 minus 8.0 is minus 5 points times 10 raised to power all over 0.01. Class, what is minus times minus? Plus, right? This minus times minus give us what? So we're left to 600 times 5 is 3,000, right? Times 10 raised per minus 5 all over 0.0015. Standard form 1, 2 is 1.5, or if you want to put 15, it can be 1, 2, 3. 15 times 10 raised per minus 3. I know why I did it this way. If I don't want to, if I don't have a calculator, 3,000 divided by 15 will give me, I think, 200. 3,000 divided by 15 is 200. Now, minus 5 minus 3 is plus 3. So that will be 200 times 10 raised per minus 2. 10 raised to minus 5 divided by 10 raised to minus 3. If minus 3 comes, it becomes plus 3, right? What is minus 5 plus 3? Minus 2. Minus 2. 200 times 10 to minus 2 means if you bring this decimal place 1, 2, you have 2.0 volts. Class, induced EMF measured in voltage. Measured in what? Voltage. Volts. Our final answer is 2.0 volts. Class, that's the magnitude of the induced EMF. That is the magnitude of the induced EMF. Take your time, alright? Because I hope it's straightforward, it's clear. Induced EMF, the answer is find induced EMF. Minus n means number of turns, they give us 600. This D means change in magnetic flux, all over change in time. Change in magnetic flux means final magnetic flux minus initial magnetic. How do you know who is the initial magnetic flux? The first magnetic flux mentioned is the initial, 8.0 times 10 raised to minus 5. The second magnetic flux mentioned is the final magnetic. So it will be final minus initial. That's 3.0 times 10 raised to minus 5 minus 8.0 times 10 to minus 5. Since they both have times 10 raised to minus 5, no need to, so I just say 3.0 minus 8 and put times 10 raised to minus 5 outside. You get? But you can do it your long method. If you don't like this, do it your normal mathematics, do everything, you still get the same. Just apply the formula. 3 minus 8 is what? 3 minus 8 was minus 5. Minus, but there was also a minus here. So the minus and minus here multiply and cancel each other. Do you get? So 3 minus 8 is minus 5 actually, but there was a minus in 600. Do you notice? So the minus and minus will give you plus and they all both go. 600 times 5 now gives you 3,000 times 10 raised to minus 5 divided by 0.015. But 0.015 is the same thing as 15 times 10 raised to power 3, minus 3. 15 times 10 raised to minus 3. Just do the math yourself, you should arrive at 2.0. Let's go to Lenz's law of electromagnetic induction. Lenz's law. States that Lenz's law states that an induced EMF is in a direction. Lenz's law states that an induced EMF is in a direction such that the magnetic field due to the current. Lenz's law states that an induced current is in a direction. An induced what? Did I say EMF? Yes. An induced current, EMF, you are still correct, don't worry. An induced current, an induced EMF is in a direction so that the magnetic field due to the current, current, opposes the change in the magnetic field that induces the current. Opposes the change in the magnetic field that induces the current. I'll come again. An induced current is in a direction. An induced current is in a direction. Class, once you have induced current, you have already induced EMF already. Remember your Ohm's law, that I and V are directly proportional. An induced current is in a direction so that the magnetic field due to the current opposes the change. So that the magnetic field due to the current opposes the change in the magnetic field that induces the current. Note, why Faraday's law helps to determine the magnitude of induced EMF, Lenz's law helps with the direction. Faraday's law, why Faraday's law helps with the what? Magnitude of induced EMF, Lenz's law helps with the what? Direction. Faraday's law helps with the magnitude of an induced EMF, Lenz's law helps with the what? The direction of the induced EMF. Write down transformers. 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 Transformer. A transformer is a device used in the power transmission of electric energy. A transformer is a device used in the power transmission of electric energy. A transformer is a device used in the what? Power transmission of electric energy. A transformer is a device used in the power transmission of electric energy. It is commonly used in the increasing or decreasing and alternating current voltage. It's commonly used in increasing or decreasing an alternating current voltage. It's commonly used in increasing or decreasing an alternating current voltage without a change in the frequency. It's commonly used in increasing and decreasing what? Alternating current voltage without a change in the what? Frequency. The transformer works on the basic principles of Faraday's law of electromagnetic induction. Class, that Faraday's law of electromagnetic induction, a good application, it could be asked in the exam, which of the following devices is an application of the Faraday's law of electromagnetic induction to transformer. A transformer, I'll come again. The transformer works on the basic principle of what? Faraday's law of electromagnetic induction. The transformer works. Class, I hope you know what the transformer I'm talking about. Transformer, the normal transformer you know now. The one we are studying something in book, we now make it look so abstract. Transformer. When you say a transformer, don't blow. That's what we are talking. All these things that we're using in real life, it is from book like this that they were made. It's from study of physics, electromagnetic induction that they made transformer, generator self. There's a software they call generator, where you study generator, study transformer. Transformer has a formula. Because you consider the primary and secondary coil, step up and step down. It has a formula. It's from book that they made all these things that you're using. Even that capacitor we did, your generator has a capacitor. I've changed the capacitor on my gen before it burns. Some of you must have heard when say the capacitor don't burn. You'll be able to produce light, right? Because it stores electrical energy. The energy that you're transmitting, that you're having light when you're on gen, is the capacitor that stores that energy that you now see light in your house. You just on gen. So these things we are doing sometimes to make it look easy to assimilate. Remember that they are real things. You know, sometimes the book has become so abstract and we just think that this is, I can never see them in this life. It's not. No, they are real things that we see every day. So if you can picture them in that way, they become more familiar and they become easy to understand and assimilate. So as I said, the transformer works on the basic principle of what? Faraday's law of what? Electromagnetic induction. Are we together? It consists of two separate coils. The transformer consists of two separate coils. It consists of two separate coils. Consists of two separate coils that are wound around a magnetic material. That are what? Wound around, W-O-U-N-D, a magnetic material. That are wound around what? A magnetic material. Two separate coils. Two separate coils that are wound around. This is a magnetic material. One of the coils, right now, one of the coils is called the primary. So the transformer has a primary and what? Secondary. Like without transformer, if they just NEPA just bring light into your house, what will happen? All your stuff will just do what? Can your light, can your devices carry the things that transformer will do, that the light will just bring directly? Just burn all your things. A transformer has to step up, step down, break down the voltage before it's sent to. So let's try and understand. It's not that abstract. Because the light coming directly from the PHY, from their grid, from their power grid, the high voltage is so. The transformer that regulates them. That's why you don't have light when transformer blow. Not that they cannot still give you light, but you can't even use the light. You just scatter all your things. As when your transformer is faulty, maybe they just broke light, just say things don't blow. Like one of my neighbor, just what happened? I don't know what kind of light they brought. That's what I mean. I like offing everything quietly. Just one kind of light they just brought. I don't know whether the transformer, they said the load on the transformer is too much. No, one thing that happens is that when a new layout, maybe a new estate or whatever is developed, there is a new transformer. Maybe only few people are staying in that estate, but people forget that people keep building houses there, right? It keeps growing, keeps growing, keeps growing. Increasing the load on that transformer. Everybody will forget. Nigeria, we don't take precautions. Normally, there's a amount of load that each transformer can carry. People keep building houses until one day you find out that the transformer that was there, that was initially put for just few houses, the whole estate is now using that transformer and is now load. There are some companies in this Nigeria that only them they have their transformer. There's people that there are some politicians in Nigeria, they just have transformer for their house. See how selfish they are. Like only their compound has transformer. There are big hotels in these companies that have just them their transformer. So that no, even if any kind of light comes, their transformer will first correct it before it sends it to them. So that's the essence of a transformer. It breaks it down without changing the frequency. Very important. So we have the primary coil and the what? Secondary coil. Now class, the primary coil has zero voltage. Voltage of the primary coil. Secondary coil has zero what? Let's call the voltage of the primary coil Vp and voltage of the secondary coil Vs. Class, because this thing was moved around the magnetic material, we have what we call Np, the number of turns. How many times was it moved around? Number of turns of the primary coil, and Ns, number of turns of the secondary. How many times was it move around the what? And the equation of transformer will now come up. We say voltage of the secondary coil all over voltage of the primary coil equals to number of turns of secondary coil all over number of turns of primary coil. Voltage of secondary over voltage of what? Primary equals to number of turns of secondary over number of turns of what? Primary. Class, there's one principle that we follow in transformer which tells us that the power input equals to the power output. Power input equals to the power what? Outputs. Hello? Yeah, just on line, please. So what are we saying? Power input equals to the power what? Output. But the power input, power is IV, remember, current times. The power input is the current in the primary coil multiplied by the voltage in the primary, and the power output is the current in the secondary coil multiplied by the voltage in the secondary. So class, as a normal rule, the power input equals to the power out. So IPVP equals to ISV. Another formula you should know about transformer. IPVP equals to ISV. Class, if ever you are asked to find the power input of the transformer, what will you need? You need the current in the primary coil and multiply by the voltage in the primary. Class, do not go and use the current in secondary to get power inputs. Secondary is output, primary is in. Please don't make that mistake. Can we take a question quickly so that this knowledge can stick to our brain before we forget it? Let us take a question quickly. Are we ready? The primary coil of a transformer has 20 turns. The primary coil of a transformer has 20 turns. The primary coil of a transformer has what? 20 turns. The primary coil of a transformer has 20 turns. Why the secondary has 1,000 turns? The primary coil of a transformer has 20 turns. Why the secondary has 1,000 turns? The primary coil of a transformer has 20 turns. Why the secondary has 1,000 turns? Are we there? If the voltage across the primary is 3 volts, if the voltage across the primary is 3 volts, if the voltage across the what? Primary is 3 volts, and the secondary has a resistance of 0.5 ohms, and the secondary has a resistance of 0.5 ohms, and the secondary has a resistance of what? 0.5 ohms. Find the power in the primary and secondary. Find the power in the what? Primary and secondary. Find the power in the primary and what? Secondary. Solution. Okay, I can even pause. I give a question. So